Hello everybody, this is Shilpa Gogre from Department of Mathematics, Mahर्षि Dayanand College, Mumbai. This is the fourth part of the videos on probability. In this video, we will see theorems on probability, or we can also call it as laws of probability. The first theorem is addition theorem. The statement of addition theorem goes like this. Let A and B be two events associated with an experiment with sample space S. Then the probability of A or B or both occur is given by probability of A union B, which is equal to probability of A plus probability of B minus probability of A intersection B. Note that union is or and intersection is and. So when I say A union B, it means elements which are in A or in B or in both. And when A intersection B is taken, it is the elements which are in A and in B, in both. The statement of addition theorem is followed by some remarks. The first remark says, if A and B are mutually exclusive events, that is, they cannot occur simultaneously. That also means that no element is common to both. And then we have A intersection B as an empty set. And therefore, P of A intersection B, that is probability of A intersection B, is 0. And hence we get probability of A union B is probability of A plus probability of B. You can look at this statement over here. This part becomes 0. And therefore we are left with only the first two parts of the addition theorem. So this can be considered as a first remark. That probability of A union B is P of A plus P of B if the two events are mutually exclusive events. Now the second remark is about the event and its complement. So A be an event and AC, that is the notation for complement of A, which is also not A, non-existence of A, that is A complement. Now you know that A and A complement are always mutually exclusive and exhaustive. Mutually exclusive means they cannot occur together, and exhaustive means both of them together makes the entire sample space S, which can be written as A intersection A complement is empty set. Therefore, the probability of A intersection A complement is 0, and because of exhaustiveness, we have A union A complement is S, and therefore probability of A union A complement is 1. Probability of S means entire space S. So it is a certain event, and therefore its probability is 1. So we get by addition theorem, or rather say by remark 1 of addition theorem, that probability of A union A complement is probability of A plus probability of A complement. That's all. But probability of A union A complement is probability of S, which is equal to 1, and therefore we get probability of A plus probability of A complement is 1. Hence, probability of A complement is equal to 1 minus probability of A. which can also be written as probability of A complement is not A is equal to 1 minus probability of A. So this is another remark. You can use any form of it as per the requirement. Probability of A complement is equal to 1 minus probability of A. Now in the third remark, extending the statement of addition theorem to 3 events A, B and C, we get probability of A union B union C is equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C plus probability of A intersection B intersection C. So this is the third remark of addition theorem. Before we go to the second theorem on probability, let us consider the concept of conditional probability. The definition of conditional probability is like this. The probability of event B, given that event A has already occurred, is called conditional probability of event B given the condition that event A has occurred, and it is denoted by probability of B given A. So we say it as probability of B and we simply say given A. So here it means A has already occurred, and in that condition we have the occurrence of B, and its probability is denoted by this notation. So the second theorem on probability is multiplication theorem. The statement is like this. Let A and B be 2 events of an experiment with sample space S. Then probability of simultaneous occurrence of events A and B is given by probability of A intersection B is equal to probability of A into probability of B given A, or we can also write it as probability of B into probability of A given B. Note that intersection is AND. So here it is probability of A and B both, that is simultaneous occurrence of A and B. Let us see the definition of independent events first. 2 events A and B are called independent events if probability of A given B is equal to probability of A given B bar, which is equal to probability of A. Note that B bar is nothing else but B complement. We have seen that the notation for B complement, that is either B, C or B bar or B dash. Any one of these notations can be used. So in this definition I am using the notation B bar. So I repeat, 2 events A and B are called independent events if probability of A given B is equal to probability of A given B bar is equal to P of A. In other words, you can understand it like this. Whether the event B happens or does not happen, it has nothing to do with the occurrence of probability of A, and therefore probability of A is independent of occurrence or non-occurrence of B. B घडू दे किंवा नाही घडू दे. घडणं म्हणजे B आणि नाही घडणं म्हणजे B बार. सो B घडू दे किंवा नाही घडू दे, A च्या प्रोबॅबिलिटीला त्याने काही फरक पडत नाही. that is why probability of A is same as probability of A given B bar, which is same as probability of A given B. Or we can also say that probability of B given A is equal to probability of B given A bar, which is equal to probability of B. So A हो रहा है या नहीं हो रहा है, इससे B को कुछ फर्क नहीं पड़ता है, B के हैपनिंग को. तो B event B is independent of event A, or A and B are independent events. And now we have a very obvious remark to multiplication theorem, which says if A and B are independent events, then probability of A intersection B is equal to probability of A into probability of B.